Today we're going to talk about a chi-squared test. Specifically, what is it and what are we going to use it for in AP statistics? All right, so here we go. First off, it is said chi-squared and not chi-squared or chi-squared or anything like that. We write it chi-squared, C-H-I, square, or squared with a D. The symbol kind of looks like an X, but it's not an X. It's the Greek letter chi. If anybody's ever been curious about why we say Xmas at Christmas, it's actually an abbreviation that the church used to use. The letter chi was used as shorthand notation for the word Christ. And so when they celebrated Xmas, it literally meant Christ's mus. Just an abbreviation there. So chi-squared. And then the formula for this chi-squared value is actually on your formula sheet for the AP Stat formula sheet. It's on the front page. And we'll talk about how to use that just in a little bit. All right, and I have a little my comic here. Remember, we are talking about chi-squared, not any sort of t, tri-t, or anything like that. So there are three kinds of chi-squared tests that we deal with in AP statistics. The first one is called the goodness of fit test, and it quite literally is to see how a distribution of a categorical variable, if that fits your sample data well. This is when you know all the percentages in this for this categorical data, and basically what we're going to be doing is, instead of saying like, I think that the proportion of successes is 25%, we're going to say, I think that here is the proportions for everything. So instead of talking about one proportion, instead we're talking about the distribution of all of them. Like, what would the pie chart look like? What would all of these proportions be? So instead of having to do a whole bunch of one proportion tests, we can do them all, basically all at the same time with a goodness of fit test. This procedure is, again, for just one categorical variable in one population. So for example, let's say that Skittles claims that the proportions of each color are the same for each factory batch. Okay, so you open a bag and you see there's 23 red and 28 orange and 27 yellow, 38 green, 33 purple. Is this evidence that the proportions are not the same? So we're getting this bag of Skittles, and obviously the sample that we have here, they are not all the same number, but Skittles claims that they are the same. So we're going to be looking at our original claim is that if you have 5 colors and they're supposed to occur the same amount, then our null hypothesis is saying we believe that the distribution of colors is 1 out of 5 or 20% for each color. So instead of just saying the proportion of red is 20%, we're saying the proportion of all of these colors are 20%. And our alternate hypothesis, instead of saying not equal to or less than or greater than or something like that, we're just going to say basically, nope, it's either the null hypothesis or it's not. And we usually phrase it like this: at least 2 of the proportions in the null hypothesis are incorrect. Now, why not at least 1? Well, it's a proportion and you're making a pie chart. So if you change one of them because they add up to 100%, it's going to cause at least one of the other ones to change as well. So they're either all right or there's at least 2 of them that are wrong, and maybe more. The other kind of test is something called homogeneity. And this is a categorical variable again. But we're going to look for 2 populations instead of 1 population. So on the previous problem, again, we were talking about a sample of Skittles. You opened a bag, you've got this one variable color for this one bag of Skittles. With the chi-squared test for homogeneity, you're looking at 2 populations. Like, I'm going to look at men and at women. And basically, instead of saying, again, that we've got, here's what the proportions look like in this one population, we're going to check to see if the proportions are the same for both populations. So for example, let's say you survey men and women, and you ask them to state their favorite movie genre. So there's your variable, like, what's your favorite movie genre? Pick from action, romantic, comedy, and science fiction. So you have this one categorical variable, favorite movie genre, and you're asking 2 different groups of people to respond, men and women. And we don't really care what the proportion is. So it's not like the goodness of fit where we want to know, could it be 25% action? Instead, we want to know, are they the same across both groups? And I noticed that the action is pretty close, but it looks like in this example, more women liked romantic comedies and more men liked science fiction. But are they different enough, proportionally speaking, for us to say that they're different? So again, our claim would be the proportions of my categorical variable. Action, rom-com, and science fiction are the same for both genders. And my competing claim is that they're not the same. The third kind of test is called the test for independence. And this is when you have one categorical variable being distributed across the categories of a second categorical variable. That basically means you have one population and two variables. So this is basically what we were doing back in chapter 1 when we studied these segmented bar charts. And we were saying, hey, I'm going to go up to a bunch of people and I'm going to ask them 2 questions. So one population, but 2 questions. And we wanted to know, if I take the highest level of education and I divide that amongst the smoking status here, does this look the same all the way across? Okay, so you randomly select adults in your hometown and you ask them how many years of education, there's variable 1, and they have after high school, and if they are a smoker, that is variable 2. Okay, and you've only got one population, the population of adults in your hometown. Okay, so the claim here is that the 2 variables are independent. The highest level of education and smoking status are independent, and my competing claim is that they are not independent. Now, mathematically speaking, the work for the chi-squared test for independence is exactly the same as the test for homogeneity. So the only thing that's different between 2 and 3 here is how you set up the null and alternate hypotheses. Everything else is identical for the 2 tests. All right, so 3 tests: goodness of fit, homogeneity, and independence. Today, we're not going to run any of these tests, so we're going to go through how to identify which one is which and the steps to do each of those in future videos. Okay, so in order to do any of this, you have to be able to calculate something called the expected counts. So the purpose of a chi-squared test is the same as the purpose of any hypothesis test. We're trying to quantify using probability, like p-values, how likely it is to get results like ours or more extreme. Oh, look, I've got a typo. Or, see, it wouldn't be one of my videos without a typo, would it? More extreme due to natural variation that comes along with sampling. So basically we're asking, do our answers not match up because of natural variation and that samples are different from each other, or do our samples not match up because something fishy is going on here? And so what we want to do is we want to see how much what we expected to see differs from what we actually observed. Okay, so the chi-squared equation is the sum of the observed value minus the expected value squared divided by the expected value. And that lovely little squared up there is going to work just the way it does with like a standard deviation calculation, in that it keeps that value positive. All right, so in theory, if what you expected to see and what you actually observed, if these 2 values were actually equal to each other, then you would end up with a numerator of 0. So if you have a chi-squared of 0, it means that you saw exactly what you expected to see. The more variation from what you expected to see, you will get a larger chi-squared value. So basically, the larger your chi-squared value, the more unusual your sample is. Very similar to a z-score in that way. The closer the z-score is to 0, the more it's like the mean. The closer a z-score is to the edge of the distribution, the larger that z-score in either direction means you have a more unusual value. So in order to be able to find this value, you have to be able to be a pro at finding expected counts, but you are already a pro. So n times p is the expected count of successes, and n times 1 minus p is the expected count of failures. So we've been doing this for 3 chapters now. You just have a few more. So when we're talking about expected counts for a sample of size n, we're talking about n times p1 and n times p2, etc. So we would just do those with all of those proportions. So let's go back to the Skittles example. Skittles claims that the proportions of each color are the same for each factory batch. So find the expected number of Skittles for each color. So we randomly selected a bag of Skittles, and here is what we observed to be true for those values right there. That's what we observed. I saw 23 reds and 28 oranges, etc. Okay, so I'd go through this and say, well, if the 5 colors are all supposed to be the same, that's 5 colors, that's 1 out of 5, that's 20% each. And I count them up, 23, 28, 27, 30, 33. We took a sample size of 150. So if I have a 150 size sample, what I would expect to see if these were actually 20% each would be 30 of each. 150 N times 20% P is 30. And since those proportions are the same for each of those, then my expected values would be 30 in each of those categories. Okay, so what about Reese Pieces? So Wikipedia states that the goal color distribution for Reese Pieces is 50% orange, 25% brown, and 25% yellow. And this is from Wikipedia, so it has to be true, right? Maybe? Okay, so you open a bag of Reese Pieces and you find 36 orange, 15 brown, and 16 yellow. So what are the expected counts, assuming that Wikipedia is correct? So again, I've got my 36, my 15, and my 16. That's what I expected to see. And those add up to 67. All right, so I know that orange is supposed to be 50% of the distribution. So if there are 67 in my sample, I would expect 67 times 0.5, which is 33.5, to be my expected number of oranges. Now, I know and you know you can't have half of an orange Reese Piece. So keep in mind that decimals are allowed in that expected value range. Okay, so you will probably get decimals there, and just go ahead and write those down like that. So brown is 25%. So 25% of 67, that's 16.75. I'm going to go ahead and write that down. And yellow is the same as brown, so that gives us that answer. All right, so in order to be able to do a chi-squared test, first off, you have to recognize you're doing a chi-squared test. And then secondly, you've got to be able to calculate these expected counts. Now, on the next slide of this presentation, we're going to be actually calculating this chi-squared value, but I'm going to do that in the second video. So meet me back here in the second video.